Hi, good morning. Welcome to this session. Sujoy and I will be talking about using NVMe-over-Fabric to do distributed scale-out storage in this session. My name is Mohan Kumar. I'm a fellow at Intel, and I've been with Intel for over 25 years. And we also want to acknowledge our friends and colleagues, Scott and Reddy, who helped us put together this presentation. So in the previous talk, you heard about PCIe and what standards can build for you. On top of PCIe, the other standard that got built was NVMe that allowed us to do storage very well. In fact, to the extent that any PCIe storage at this point is probably is an NVMe storage, and Devendra showed the numbers in terms of the CAGR of the growth of those things, right? There is also distributed scale-out storage. What do we mean by that? Things like Ceph, things like Hadoop. There's a bunch, and then there's a bunch of proprietary ones that are not open source as well. And the question is, and there is also another protocol, I'll go into it, which is NVMe-over-Fabric, which is the ability to carry NVMe on top of some fabric. The fabric today is basically Ethernet, but it could be either TCP or RDMA or InfiniBand, but I know they have the definitions for both Ethernet and RDMA fabrics today, right? So it's one of those cases where the solution that if you take scale-out storage, NVMe and NVMe-over-Fabric together, the sum is greater than the parts, essentially. That's our thesis, and we hope that you will agree with us by the end of this presentation. Before we jump into it, we want to give you an overview of what NVMe-over-Fabric and what a distributed scale-out storage is and what the issues are. And then Sujoy is going to talk about various options to fix the problems that you have today with distributed scale-out storage, and why what we propose is a better solution for this problem. So if you think about NVMe-over-Fabric, it basically, like I said, builds on a bunch of NVMe drives connected to storage nodes, right? And essentially some host can access this over the network, and it has the ability to essentially materialize these as drives. As far as this host is concerned, or any of these hosts is concerned, they look physically connected to them. It's composed storage, right? So when from a standpoint of their drivers and everything, and their software, it looks like it's locally attached to them, right? They don't know any different from an NVMe onwards, right? NVMe, the block layer, everything sees this as an NVMe device with a namespace and a certain capacity. And what that capacity you can construct by this NVMe or protocols management layer to say, and what it allows you to do, take a drive that maybe say it's 1 terabyte at the bottom together, and then essentially split it out into two different hosts, or go the other way, right? It allows you to do all those neat things here in terms of what you're able to materialize. And the reason for going down this path as opposed to doing a software-based mechanism is that it's very low latency. It's essentially built on top of, like I said, Fabric today is defined by as Ethernet and RDMA. And at a one stack level, you're probably looking at like tens of microseconds latency in order to access it. And if you want to compare the device latency of like a 4K block being transferred, if it's anything NAND related, it's probably in the 70 to 100 microseconds. So 10 microseconds is, it's like 10% of what your actual device latency is, right? And it's high performance as well, right? Because there is not a whole lot of overhead. It allows you to do 1:1 mapping. Essentially, you can take this drive and completely assign it, or you can take some storage nodes entity and then completely assign it to particular host. And then from an initiator standpoint, this is one of the ways in my mind both PCIe and NVMe and now NVMe-Fabric win, is because they have a well-defined mechanism in software to make this work, right? So essentially what you do is in the host you have the NVMe-to-Fabric driver that sits below the NVMe driver, and then everything else is just completely transparent to software. So you don't go around keep changing your software layers all the time to access it, right? And then lastly, it's the theme of this conference, and I guess, is that it's a standard interface, so it's got broad adoption essentially, right? So if you look at Linux has got an NVMe-over-Fabric driver. The other vendors are planning to support their version of NVMe-over-Fabric driver. So once you have the driver, everything just looks and acts like there is an NVMe device, and no software above that layer needs to know, right? So that's on. So yeah, that talks to the widespread industry adoption. I wouldn't say widespread yet. I mean, it's getting towards there. Linux definitely has it. The other OSVs have announced at least plans for supporting it either this year or next, essentially, right? So, but the point is that this will be widely available. Much of this is today on RDMA, like I said, Rocky and IWARP. There is also a definition for doing this on TCP/IP for things that once you go to TCP/IP, your latency will, you don't have the performance guarantee. But then the idea is that people want to do NVMe-Fabric with things that are like what would have been a SATA drive, for example, right? Collect cluster of SATA drives that they want to transport, abstract and transport as on top using NVMe protocols. So and then switch to connecting this to the main topic of today, distributed scalar storage. So think Ceph, for example, right? Again, the pictures look similar, but I want to show you where they will start diverging as well, right? You'll have today, as Devendra was pointing out in his earlier session, right? Many of these are PCIe and NVMe based SSDs as we go into the now and into the future, and these things are attached to storage nodes and a bunch of storage nodes. This is the scale out portion of it, right? You can scale your storage capacity by essentially adding more storage nodes and more drives into the storage nodes, right? That's what things like Ceph does. And then each one has a solution specific. Like this year, you have you have your libRedos or your software layer that essentially understands your specific storage protocol, right? If it's Ceph, it is Ceph. If it's some other protocol, you have some piece of software that then allows you to get a block allocation from this thing. So the concept of taking these hardware with storage and turning them into a block abstraction is a combination of this and then the combination of these green boxes here, right, essentially. And it gives you all the virtues that you would like from any storage software, right? It gives you availability because one of these nodes could go down because it gets distributed. It gives you performance by having multiple copies and being able to access them from whichever copy is the most efficient for you to get access from, and the protocol. They define the protocol for optimizations. Like I said, in NVMe-Fabric we kind of pick RDMA and now TCP. But in this case, the vendor gets to define what protocol they want to use to communicate between, because it's their client and it's their server. So both ends they control, so they can define the protocol that they do. And of course, you have both open source like Ceph, and there's some closed source stuff. I don't want to pick a name, but there's a bunch of them out there that do the same, right? So what's the problem with this type of a solution? First of all, the problem is that you need to go write a driver or a client for client software for each operating system, each hypervisor that you end up having to support, right? And then each one has its own solution-specific management, right? It's not so much at the storage node layer, but at the client node layer, right? You need to do management that's very specific to whatever stack it is that you have signed up for, and you're bound to that stack. And then that's what it's talking to, right? The host essentially gets very, very tightly coupled to your storage service because you have to deal with the lifecycle management issues, right? You upgrade something, you can't just do isolated upgrades, right? You have to deal with the client impact of whatever you're doing at the server end. And essentially, the clusters, any issue you have at your storage node cluster essentially extends to your host also, because your host is as much impacted by, because it's got this client software that fully aware of whatever storage stack like Ceph that's running underneath you. And then last but not least, it may take footprint from your host, right? And this is more of a, with the emergence of cloud and private cloud, if you're running a host and you're running some services, VMs, containers, functions, you name it, right? Your primary goal is to essentially optimize that host for delivering that thing, whatever you're running, right? You don't want, everything else is essentially infrastructure or context to what you need to deliver, right? You don't want your context to consume too much of your resources, right? And depending on what scale-out storage you're running, it's going to take valuable resources away from whatever you want to use it for, your application layer, your VMs, containers, and so on, right? And then there is a push these days to essentially just to solve the problem of, I bought the host to run some application or run from my VMs or containers, so I really don't want my host to be doing my contextual stuff. So what do? I take my contextual stuff and offload them to what's called the infrastructure accelerator, right? And there is FPGAs, SoCs are emerging to fill that gap, and large cloud companies are doing their own, right? So, but in order to, if you're going to do something like that, then it needs to be fairly small footprint, because otherwise this is not going to work out, right? If you're going to say, let's say there are three scale-out storage stacks that you want to support, and all three of them you need to expose whatever abstraction they have, and their storage software has to run in your infrastructure accelerator. Now you're essentially multiplying the problem to the point where the accelerator part of the is no longer true, because it's going to have a hard time. It's basically becoming a host in itself. So that's kind of the situation that we are in right now, in terms of where we have this valuable technology and the status quo on the scale-out storage software. And the question is, what do we go and do essentially to bridge the gap and take some of the pieces that we have in standards-based solutions and convert them into a solution for this problem. And to give you more, I'm going to let Sujoy cover the rest of this.
Thanks, Mohan. So as Mohan mentioned, I'm Sujoy Sen. I work at Intel as well, and I've been focusing on storage and I/O disaggregation and pooling in general, technologies of pooling over fabrics, over Ethernet primarily, but other fabrics as well. So Mohan sort of set the stage for what the problem is that we're trying to solve, which is really try and provide a standards-based interface, an NVMe specifically, to various storage services that exist, right? We're sort of targeting scale-out storage as a good poster child for this, because that seems to be emerging as a class of storage service that's getting used quite a bit. But there could be other set of storage services as well. But what we really want to do is provide a standard interface in front of it, right, to solve all the issues that Mohan brought up in the last foil. So I'll talk about, maybe spend a couple of slides on what can be done today with things that are available today, what some folks are doing today, and then some of the issues related to that, and then get into what our particular proposal is to solve this. So obviously, if you want to put a standard interface or some interface in front of something that doesn't support that natively, you do what any good computer scientist does. You employ indirection, right? So in this case, you introduce the concept of gateway that exposes NVMe, to the host. Uses NVMe-Fabric, or it could be iSCSI, if that's the desired end state. to a gateway node, and that translates to, that has the custom client that can go and talk to the actual storage service below, right? So you get the benefits of a standard client on the host, the footprint associated with it, and more importantly, it decouples this with this, right? Decouples the host from the storage service as much as possible, right? So it brings in all those goodness, but then of course you increase latency, so you reduce performance. You have extra hops. The gateway can become a bottleneck depending on your workload and I/O patterns. And of course, your management complexity increases because now you have one more extra component to manage. Right? So all good. Depending on what you want, that may work. So next thing you can do is, well, I'll add multiple gateways. So that alleviates my bottleneck at the gateway. And I can now use load balancing and other techniques to map my volumes on the host and distribute them to different gateways and let each gateway handle a subset of the volumes. This works really well to support a large number of hosts and a large number of volumes. Of course, you still have the extra hop latency issue, right? Because you're still going through a gateway to get to your actual storage services. But depending on, again, your workload and your volume access patterns, it is still possible for a particular gateway to get overloaded, right? And then you can bring in orchestration complexity, use telemetry to sort of move these assignments, and you can get really sophisticated with what you're doing. But at the end of the day, that just increases more complexity in your management. And because you're adding multiple gateways, physical or virtual doesn't really matter. It does add cost to the solution. So the next obvious step is, well, why have separate gateways? Why not just integrate them into the storage nodes themselves? And that works. You get rid of one layer of machines. Again, physical or virtual doesn't matter. But your latency really doesn't change, right? The extra hop latency you still incur, because at the end of the day, all the volumes, all the IOs to a particular volume end up on one particular node first, before getting distributed, into the storage layer itself. And again, that bottleneck that was occurring here on, when we had separate gateways, simply moves down to the storage node. And in many cases, the storage node is CPU heavy, right? And anything you take away, any resources you take away from the storage node in processing this gateway functionality is basically directly affecting your storage performance that you deliver to your clients. So what would be nice is if we had this integrated gateway concept, but it was distributed, right? This goes back to the original DSS picture that Mohan showed, which was, hey, I have a volume. I want to get to the correct node right in the beginning, right from the get-go, right? But instead of having this custom sort of client here, I want this to be NVMe, right? This is really the end goal that we're trying to achieve, which is good. The question is, what does that mean? So the first thing it means is it requires these volumes to be aware of multiple targets, right? Today with NVMe-Fabric, multipath notwithstanding, primarily it is a one-to-one relationship, right? One volume is mapped completely to one target, to one subsystem. You can have multiple subsystems. The idea, though, is that's really for multipath, right? It's not really aware of a volume mapped, different LBA ranges being mapped to different nodes. And that's one thing that, that's one change that's required, right? The second one is, well, how does this guy decide, the client decide how to place the data, right? Because the storage service that runs here, there's various, Mohan said, there's open source versions, there's proprietary versions. So it's very hard for the NVMe interface here and the NVMe device here to support all of them, using one scheme. So the placement scheme that this needs to use has to be extensible, right? So it's something that can be extended to support multiple storage backends here, right? The other thing that really is needed is, this architecture will decouple, the NVMe with the storage nodes here. But the problem is management, right? Every time something changes down here because of either a failure that, where it's trying to recover from a disk failure or node failure, and it's changing its placement around, or it's trying to load balance because of performance, which all of these scale-out storages do, you're affecting the interface up here at the host. And that brings in management complexity. So this extension that we're talking about in terms of placement really needs to be, to have, the least amount of management intrusion, right? So that's really the end state we are looking for. Now the question is, how do we get there? So what we thought was, let's come up with a solution that gets to that end state using NVMe and NVMe-Fabric as it stands today, right? And basically, if you remember, we need NVMe or Fabric to be aware of multiple targets. We need a way to extensively figure out where data goes. And we need that management complexity to go away so that these two can truly be decoupled. So for the last part, we want it to be self-learning, right? So we sort of took a leaf out of the internet routing world, where even if you get a route that's not exactly accurate, packets still get routed, but eventually the router learns. So we sort of want to take that concept and apply to this solution. So what we're doing is we're proposing the two concepts of a redirector and hints into this NVMe-Fabric sort of solution. What a redirector basically on the initiator side and on a target side does similar things. On the initiator side, a redirector gets the I/O and figures out where, for this I/O and for this namespace, where it should go to. And it looks up some table, which we call the hint table here, to figure that out, right? When a target sort of gets an I/O, the target redirector figures out if it should service it itself, because it's a redirector that's specific to the storage service, or if it doesn't own it, should it just send it to somebody else who does own it. But the main thing is, even if the I/O goes to the wrong target redirector, that target always has to complete the I/O. So there's no error back to the initiator. So that way, that ensures the weakest coupling, if you will, right? The storage service is free to move things around without the initiator getting impacted. You can, so even if the initiator gets it wrong, the storage service, the redirector, will take care of it, right? And complete the I/O, right? So in this case, the I/O one flows through. The initiator doesn't know where it should go to. It sends to a default redirect target. This guy sends it to the right one, completes it. And then the second concept of hint comes into the picture, where now the first redirector sends a hint back to the initiator saying, hey, for this I/O, this is really where you should be going. And the initiator learns from that hint, populates its hint table, however way it wants to implement it, right? So the next time an I/O comes to that LBA or that range, it goes to the right target, right? So with this scheme, you basically have an initiator that eventually learns where, learns about the placement, right? That's the basic idea. And the storage service is sort of free to do what it's doing, right? Because once it gets at I/O, it services the I/O as if it just came from its clients. So then the question is, what do the hints look like, right? So as I was saying, that we want to be able to, these hints are this primary mechanism by which a host is told where data is placed, right? And this needs to be extensible, right? It needs to support a wide range of placement schemes that different solution stacks provide, as well as it needs to be extensible for new things that are going to show up, right? So what we sort of came up with is 3 categories, and this, of course, I suspect more will be added to this, but 3 categories of hints to take care of different kind of known backends today. So you have, sort of simple pairwise backends, right, where you're basically mapping a volume across just 2 nodes and replicating it, right, to where you have slightly more sophisticated placements where extents are taken from a set of nodes to create a volume, and then within that replication is done, or erasure coding is done. Then you have backends that do sort of more RAID-like striping, right? And then, of course, you have backends like Ceph that do algorithmic level-based placement, right? And so what we thought was, if you categorize all of that, there's sort of 3 schemes of hints, right, that we can support. One is simple hint, which is really a range of LBAs mapped to a set of targets that an LBA maps to, reads and writes separately. And again, a set of targets, because for reads you may want to give a priority, or a set of targets that the reads can go to if you want to parallelize the reads. But for writes, maybe you want to give an ordered list of targets because of the primary replica versus secondary. So that's what a simple hint does. It takes care of extent-based mapping. It takes care of pairwise HA sort of solutions as well, right? The second one is striping hints, which are, as I said, backends that would support things like RAID 0, for example, right? Again, here the idea is that you give sort of a LBA range, what extents it maps to, what kind of striping group it's part of, what's the stripe size, and that allows the initiator to just calculate exactly where a particular LBA access needs to land. And then the last is the hashing hint, which is where the hint really comprises of the hashing function that needs to be used, the way an object, because usually, like especially if you take something like Ceph or Gluster, you derive from the volume name and the LBA, you derive an object name, an object ID, you calculate a hash function on it, and then you go look up a table to figure out, basically a hash bucket table to figure out which node it needs to go to. And that's what, all of that is embodied into the hashing hint, right? So what kind of chunk size this scheme uses, right? What is the object name format that this scheme uses? Predefine a bunch of hashing functions that are common, and I'm sure that can be extended. And hashing table location where the actual lookup is for the actual node. Right? And these three together, essentially, we think, depending on which one you get to use, or you can combine the two, depending. You can do a hashing hint, but sometimes you get the wrong node because the backend is changing things around. So you can add a simple hint, a specific location hint on top of a hashing hint. That'll take precedence, right? So you can do these things to always minimize your latency, get to the right node as quickly as possible, yet allow this thing to learn as the storage service is expanding, contracting, changing its placement. So if you have to do this, what are the changes to NVMe-over-Fabric that needs to be done? So our first premise really is that we want to reuse the existing elements of NVMe-over-Fabrics, right? Try not to introduce any new, as far as the protocol and the architecture is concerned, not try to introduce any new element, anything radically different, right? And that's what we set about doing, trying to see, can we just do this using existing elements? That doesn't mean existing implementations will not have to be changed. Of course, you have to implement a redirector. You have to be able to implement, paying attention to the hints, using the hints to go to the right place. But at least from an NVMe-Fabric protocol standpoint, we get to use as much as existing elements that it already provides. Also, it was important that legacy initiators continue to work with storage services that have this redirector capabilities. So what I mean by legacy initiators is, we all know that once you have a standard out there, and Devendra talked a lot about compliance and interoperability, NVMe and NVMe-Fabric is certainly taken in a big way. Lots of products out there, lots of native support from operating systems and hypervisors. So you'll have initiators out there when you deploy a storage solution with this capability that still need to work with the existing initiators. So we want to make sure this is backward compatible. And basically what makes it backward compatible is the fact that an initiator doesn't pay attention to hints, can still send an I/O to what it thinks a node is the right node, and that node will complete the I/O. It'll figure out where the I/O actually belongs to, send to that node, get the results, and send it back at the expense of performance, but you'll continue getting functional capability. That's why it was even more element that we use the NVMe-Fabric elements. So there are three sort of things we need to worry about. One is what are the hints? How do we represent hints? How do we notify hints? And how do we know that a particular NVMe-Fabric initiator or target, but mostly it applies to target systems, is capable of this functionality? So the first thing, how do we represent hints? Well, we figured log pages are a good way to do this, right? NVMe already defines the concept of log pages, both there are standard log pages as well as you can do vendor-defined log pages. And that's a good way to basically deliver hints, right? So all of those hints I talked about can map to different log pages and different formats. Right? Of course, things like when somebody is reading a log page, it needs to be consistent, as a log page might be read in multiple chunks. So things like that have to be taken into account. But the concept of log pages can be used for this. The second thing is, how do we notify that there is a hint? That hint propagation thing that I showed earlier. AERs are a good way to go do that. Your asynchronous event requests, that's already supported by NVMe or Fabrics today. So you can have an AER outstanding for the particular log page that you're looking for. So the initiator can send an AER, and whenever there's a log page that affects that initiator, the target can send a completion back, and that causes the initiator to come back and read the log page. So that scheme we should be able to use that scheme to do the notification. And then capability discovery is probably the easiest. We think either the supported capabilities in the get features commands, we should be able to add bits to it to allow for initiator to discover redirected capability targets. Until that's there, you can use a whitelist or some other schemes to sort of at least get the ball rolling. So in summary, and Mohan sort of started with this, right? What we're really saying that any distributed storage service, and as it was probably obvious, we're focusing on distributed storage service, but we're really looking at any storage service, I think can benefit from a standards-based interface into the host, right? I think SNE has been doing, that's really what SNE has been driving a lot, standards-based interface. From the earlier talk, we know that with standards, there's innovation that we can leverage from a large body of work. So what we really want is provide a standards interface to any storage service, right? And we believe any storage service will benefit from this approach, right? So once they develop their service, they have a ready-made ecosystem that they can just plug into, and they'll be able to deliver their service straight to the host right away. NVMe, of course, we feel is the ideal interface. It's it's obviously gotten a lot of ground. It's got a lot of ecosystem support already, and so that seems like the right place to be. Because now there is a network component, a fabric component to this, that we believe NVMe-Fabric fits that bill naturally. It already has the elements needed to make such a scheme work. So in total, between NVMe and NVMe-Fabric and marrying it to any distributed storage service, we feel that we can deliver sort of the best experience to a customer as far as storage is concerned. And the table here kind of just captures everything that we said in the last 45 minutes or so, which is you have a distributed storage service today, and it suffers from a lack of standard host interface. It, of course, delivers good performance, right? And of course, the gateways aren't applicable to it. Then you add, the gateway, a single gateway, distributed gateways, and gateways exist with, AWS gateways, Azure gateways, other gateways, but they bring the goodness of a standard host interface, but both in terms of availability and performance, then, they basically bring some, badness to the original distributed storage solution. With this self-learning NVMe-Fabric solution, in general, we expect that you restore the goodness of DSS, but you bring in the goodness of a standard interface. So thank you. Questions? Sorry, go ahead.
How does stuff like reservations in a
So the question is, how does things like reservations and something like how will that be supported here? Well, if you notice from an NVMe standpoint, it is still, from a host model, it looks like the same, right? You have a volume that is surfaced on the host. You send reservations to it. You need to have the NVMe-Fabric target support reservations to begin with. Even today, if you don't have the scheme, it always gets to a target first and then gets to the right node in the storage service. So if the storage service supports reservations, the reservation just flows through, right? This doesn't add any new complexity there, right? Sorry, let me just get your question.
A lot of what you described is a software-defined storage architecture that's already implemented by a lot of upper layers, a lot of systems. Who do you see actually shipping the things you propose here? You seem like you're trying to push it way down to the bottom of the stack. Is this devices, appliances, operating systems, what?
Yeah, I think what we're trying to do is, I think, as we said, push it down to at the NVMe layer as far as the operating system is concerned, right? So you don't need anything on the host that's higher than that's managing this, right?
Yeah, I see.
And have the storage service that's typically running elsewhere not worry about how that's getting delivered to the host as long as they have the right thing. That's sort of the basic idea. Question?
So 1 second.
Yeah.
Let me. So the one thing is that we see, if you think of scale-out storage, I mean, they're solving different set of problems really well. But if you look at a scale-out storage software, the volume management, snapshot, all kinds of functions that are built into it, and they do really, really, really well, right? But then you're kind of in the client. They feel obligated to put in a client interface with their backend essentially. By doing, and then NVMe-Fabric, if you look at it, essentially says, I'm going to help you disaggregate storage, but then it doesn't do any of these things that you would expect any storage service to do. So what we're saying is essentially the hybrid approach basically lets you keep your storage backend, but then provide you an NVMe front end. So the host burden goes away. The host burden gets to be a standards-based solution, and essentially it's a pieces of software that you create on top of the backend to essentially provide the translation and, more importantly, the management matching, right? There is this management layer that has to say, I'm going to create a volume, take that volume, map it into an NVMe-based thing. Now it shows up as NVMe, and then the NVMe management or Fabric management takes over.
I still don't fully understand who's going to provide all those things. The devices, the gateways, what the heck are those,
So, for example, so let's take Ceph, right, because it's open. I can see where Ceph provides this as a variation of Ceph essentially that does this. So it comes from the storage nodes up, and then
so Red Hat will ship this.
Whoever is the vendors.
Right. So you basically, somebody has to develop the on the storage nodes the right redirectors, right, with NVMe-Fabric on top. But on the host side, it will be standard NVMe initiator drivers that will have to support this, right?
Something similar to the security question, not only from a sanitary point of view, but from a device locking, TCP Opal, that type of thing. How does it work in this
Yeah. So this doesn't change any of that model because, again, if from a host standpoint, you see an NVMe device. And if you did TCG in Opal, if you expected Opal support and you were using it as Opal, you still get to use it because that just gets to, again, the storage service. And the storage service, of course, has to support the Opal standard. The targets have to support the Opal standard, which is true today. I mean, for any NVMe-Fabric solution, the targets have to support the Opal standard. And so this just brings that to the table. Right. There's nothing. I don't think the basic device model that NVMe and NVMe-Fabric brings to from a host and application standard, whether it's reservations or Opal, doesn't change. Right. ultimately it has to be supported by the backend regardless of how you deliver it. Great question.
So would this require any changes to the NVMe-off-Fabric specification?
Yeah, so we don't, like I said, all the elements exist, log pages, AER, supported feature bits. So, we're prototyping with obviously just vendor-defined things right now. Once all of this gets sort of worked out, we can standardize the log page information, for example, right? Like, okay, log page XYZ is for hashing hint.
Yeah,
and this is the hashing hint format, right?
It doesn't change the protocol of NVMe-over-Fabric. It's the management portion of it that's going to change.
Question?
It still doesn't enable multipathing.
Well, current multipathing would work. Native NVMe multipathing that's now in the kernel will continue working. Sorry, question?
So rather than distributing the hints, have you considered keeping them in a central location rather than even maintaining consistent?
Sorry, can you repeat the question?
Rather than distributing them across redirectors, the hints and all those things, have you considered keeping in a separate server?
Yeah, I think one of the main things we're trying to avoid is, especially to support large scale, is having central management as much as possible. So all the goodness that a distributed storage system brings is that. And so if you distribute it, we think, from a self-healing standpoint, it's going to scale better. But yeah, you can implement something that's more centralized as well. I mean, I don't think this is mandating a particular kind of implementation. Because the hints can come from, like Mohan said, it can be a management solution, right? Any other questions? No. Well, thank you very much for your time.